Hi everybody, I hope this video finds you well. In today's video, which will be the last of our content videos, we're going to be doing one more example of running the ANOVA hypothesis test that we introduced in the previous video. So we'll take a look at this example, run through all the sort of details here, and then also build one confidence interval as part of sort of a review of the older material that we've been discussing. So let's jump right in and talk about this example. So we're going to suppose you want to study if there's a difference in the average reaction time for adults of different ages. So to study this, you randomly select some adults who are between 20 and 30 years old, 40 and 50 years old, and 60 and 70 years old. You then give each of the subjects a reaction test and record their reaction time in milliseconds. So you get the following data. So just to make sure we understand sort of the data here, right, we can see that for the 20 to 30 year olds, we had somebody who reacted in 220 milliseconds, 300 milliseconds, all the way up to 630 milliseconds. For the 40 to 50 year olds, we had somebody who took 280 milliseconds all the way up to 730 milliseconds. And for the 60 to 70 year olds, we had somebody who took 290 milliseconds all the way up to 970 milliseconds. Now, do keep in mind when thinking about reaction time, right, the lower the reaction time, the faster your reflexes, right? So if it takes you a really long time to react, that means you actually have slower reflexes. So we've got these three sets of quantitative data here, and the first thing we'd like to do in part A is carry out at alpha equals 0.05 a hypothesis test to test the claim that there is a difference in the average reaction time for adults from these three different age groups. Now, before we get into running this hypothesis test, which is going to be an ANOVA hypothesis test, how do we know that it's going to be an ANOVA hypothesis test? Well, we know that this is going to be an ANOVA hypothesis test because what type of variable are we studying here? Well, we're looking at reaction time, which clearly is something that is quantitative, right? We also know it's quantitative because all throughout we see the mention of the word average, which only relates when we have quantitative data. So average reaction time there, and we're talking about whether or not there's a difference in average reaction time. So we know we're working with quantitative data. And how many samples do we have here? Well, we have 3 or more samples coming from 3 or more different populations. So all of that makes it an ANOVA hypothesis test. Before we jump into actually running this test, though, I would like to just mention why we bother with an ANOVA hypothesis test rather than several individual hypothesis tests. Somebody could say, why don't we just use the 2-sample mean hypothesis test, which allows us to compare 2 samples a couple times. We could do a 2-sample of the 20 to 30 year olds versus the 40 to 50 year olds. Then we could do a 2-sample of the 20 to 30 year olds versus the 60 to 70 year olds. And then we could do a 40 to 50 year old versus 60 to 70 year old. So we could do like 3 different 2-sample mean hypothesis tests. Well, obviously, one argument against that is that, well, we'd have to run 3 different hypothesis tests. So that doesn't sound like a particularly pleasant sort of amount of work that we'd have to do. But there's actually a deeper reason why we avoid doing that. We have to remember that anytime we carry out a hypothesis test or we build a confidence interval, we have the potential to make an error, right? We've spent a lot of time sort of introducing and discussing type 1 and type 2 errors. And we know that every time we run a statistical procedure, we expose ourselves to that potential of making an error. Well, what that means is that if you were to analyze this data using 3 separate hypothesis tests, 20 to 30 versus 40 and 50, 20 to 30 versus 60 to 70, 40 to 50 versus 60 to 70, right? You'd expose yourself to 3 opportunities to make an error, as opposed to just a single opportunity. And this is basically something in statistics that's called the risk of repeated testing. In other words, by having many tests, you expose yourself to higher and higher probabilities of making an error. That's why we make use of these global hypothesis tests to sort of start our analysis, because they bring it all into a single test. So that's why we're looking at this ANOVA hypothesis test here, rather than sort of doing everything pair by pair. All right, so we know that we're going to be running this ANOVA hypothesis test. Let's go ahead and set up our hypotheses here. So for step 1, we'd like to see what the hypotheses look like. So we've got our null and our alternate. We know that for an ANOVA hypothesis test, the null is always that the populations are all going to have the same average. So we'd say that the mu for the 20 to 30-year-olds is going to be equal to the average for the 40 to 50-year-olds is going to be equal to the average for the 60 to 70-year-olds. So in other words, our baseline assumption is that our three populations are all going to have the same average. Our alternate is, again, that at least one population average is different. Now, again, that could mean that all three of them, that this is not equal to this, is not equal to this, or it could mean that maybe these two are pretty similar, but this guy is very different from those two. Again, this is a global hypothesis test, so it's just making a general statement that there's at least some difference here. All right, remember that when running one of these ANOVA hypothesis tests, the majority of your work is going to be in checking the conditions. So we'll go ahead and move on to that here. So talk about the conditions. We need all the samples to be random and representative, and that was stated that we just took random samples of adults of different ages. We also need all samples to be less than 5% of their population sizes. The only thing we need to be careful about here, I mean, obviously the adult populations are absolutely massive, is to specify that we do have three different populations here. So we can just say lots of 20 to 30-year-olds, definitely. Lots of 40 to 50-year-olds, definitely. And lots of 60 to 70-year-olds, definitely. So we're all good. All right, condition 3, this is the one that we do whenever we have quantitative data. It's about the data either being approximately normal or having more than 30 in each sample. Well, if we look back here, clearly, right, each of these data sets is pretty small. We don't have any of the data sets being greater than or equal to size 30, so we're going to have to actually check that each data set is approximately normal. So we need to check that the data is approximately normal. Just to make that a little bit easier, I think we'll go back up here and do that here so that we can sort of see our data as we're building it. So let's do one for the 20 to 30-year-olds. Right? So looks like we can do this where we sort of ignore the 0 at the end because it's always 0 and just stem and leaf plot the first two digits. So for the 20 to 30-year-olds, it looks like we need stems of 2, 3, 4, 5, and 6. And then we have 2, 2. 3, 0, 3, 4, 4, 0, 4, 1, 4, 5, 4, 6, 5, 0, 5, 5, 5, 8, and 6, 3. And that guy is all good, right? There's no strong skew, no outliers. Everything's looking pretty decent there. For the 40 to 50-year-olds, we can do a similar one, though we'll need a 7 stem as well. So we'll have 2, 3, 4, 5, 6, and 7. And then it looks like we should have 280, 300, 320, 400, 460, 470, 500, 510, 520, 630, 680, and 730. And we're all good there as well. Again, you know, maybe not as tall of a central peak as we would expect, but generally pretty symmetric, no outliers. We're all good there. And then finally, the 60 to 70-year-olds, looks like their stems should go from 2 to 9. So 2, 3, 4, 5, 6, 7, 8, 9. And looks like we've got 290, 350, 430, 550, 580, 600, 630, 650, and 670, 730, 740, 850, and 970. And again, maybe this guy's got a little bit more of a tail off to the left, but again, reasonably normal, no strong skew. It's not all piled up here with a long tail off to the left. So this looks pretty reasonable. We're all good. Again, we're able to use the same key for all these, so we'll just include one key. 2/2 here actually meant 220. So condition 3 is good. All of our samples look reasonably normal, so we can sort of assume each population was reasonably normal. So we're good with condition 3. Then for condition 4, this is the one that says that the population standard deviations have to be equal. Of course, we can't actually look at the population standard deviation, so we're going to check that the largest sample standard deviation is less than 2 times the smallest. So we're going to look at the max sample standard deviation needs to be smaller than 2 times the minimum sample standard deviation. So at this point, we need to know those sample standard deviations. So it's probably time to start typing all this stuff into our calculator. We'll put the 20 to 30-year-olds in L1, the 40 to 50-year-olds in L2, and the 60 to 70-year-olds into L3. And we'll go ahead and use our one var stat for each of these to get the relevant information. So if you do one var stat on L1, of course, right now for this condition, all you need to record is the S, but it doesn't hurt to just be prepared for later things like a confidence interval or something like that and record the average and the sample size as well. I mean, if we're typing it in, we might as well get everything we might need. So we can see that the X bar for this group is 440. The sample standard deviation is approximately 123.5, and it looks like we had a sample size of 11 20 to 30-year-olds. Then you can do your one var stat, but now applied to L2, and you can see that the average for the 40 to 50-year-olds was approximately 483.3. The standard deviation there was 145.4, looks like. Yeah, 145.4. And the N was 12, so it looks like we had 12 40 to 50-year-olds. And finally, for L3, we'll use our one var stat, and we'll make sure that we switch it now to L3. And looks like we should get an X bar of approximately 618.5, a standard deviation of about 189.3, and it looks like the N here is 13. So we've got all of our mean, standard deviation, and sample size for each of these. Again, for condition 4, you just need these sample standard deviations, but doesn't hurt to just write down everything so you don't have to go back and redo the one var stats later. All right, do keep in mind you're also going to need to put the data into L1, L2, and L3 anyway to run the ANOVA test, so it's good to just do everything here at once. So the maximum standard deviation looks like it came from the 60 to 70-year-olds. Notice that makes sense because what is standard deviation doing? It's measuring the amount of variation or spread, and you can see that the reaction times for the 60 to 70-year-olds were all over the place. Right, there was somebody who was as low as 290 and all the way as high as 970. So it makes sense they had the highest standard deviation. That's just a reminder of what standard deviation is really measuring. So we can plug this stuff in and confirm 189.3. Is that really smaller than 2 times the minimum? Well, it looks like the smallest one came from the 20 to 30-year-olds, which was 123.5. So 2 times 123.5. If we check that, 2 times 123.5 on your calculator should come out as 247, and 189.3 is indeed smaller than 247, so we are all good. So condition 4 is satisfied as well. All right, now we are ready to move on to steps 3 and 4. This is going to be our test statistic and our p-value. So this is where we're going to use the ANOVA of L1, L2, L3, and then close it up with parentheses. Remember that to get the ANOVA, you're going to hit your stat key, go across to tests, and then go all the way down to where it says ANOVA. Hit enter, then put in L1, L2, L3, and then close up the parentheses. And then you'll want to record 2 things from that. First of all, we want to grab our test statistic, which is an F statistic coming from the F distribution. The F statistic here is approximately, and we'll just record 2 decimal places, I guess, 4.30. That's what we usually do for statistics. And then for the p-value, looks like that comes out as approximately 0.0219 after we round. So there's our F statistic and our p-value. Now you might ask yourself, why do we need to bother writing down the F statistic? We really don't in this case because the calculator is also giving us the p-value. But just so you guys sort of stay consistent, in all the other tests we've done, we always write down the test statistic and then look it up on some table. Since all that's being condensed, it's not really necessary to put the F statistic. But again, just for consistency, we will record both the F statistic and the p-value here. All right, then we are ready to go ahead and make our conclusion. So we can take this p-value and compare it against the alpha, that is 0.05. How does this p-value compare? Well, this is about 2.19%. This is 5%. So our p-value is coming in smaller than alpha. So we have a small p-value. So we observe something that was very unlikely to happen under our null assumption. So we are going to reject our null hypothesis. That means we have significant evidence for our claim. Well, what was our claim? Well, if we look back up here, we're rejecting that all the population averages are equal, and we are saying that we have evidence that at least one population average is different. So, significant evidence that at least one age group has a different average reaction time than the others. All right, so we're saying that at least one of these groups, at least one of the 20 to 30-year-olds, 40 to 50-year-olds, or 60 to 70-year-olds has a different average reaction time than the other groups. Could be that they're all different, could just be that one of them is different from two of them. Don't know. We just know that there's at least some difference amongst these three age groups and their average reaction time. Okay, so this is your guys' second example of running one of these ANOVA hypothesis tests. Again, in terms of the work that you need to be showing, the majority of that work is in writing out the conditions here because the calculator is going to take care of the test statistic and the p-value. Let's do a little bit of a follow-up with this and try to build a 95% confidence interval for the average difference in the reaction time for 60 to 70-year-olds compared to 20 to 30-year-olds. Why would we do this as a follow-up? Well, we just found that there's evidence that there is some difference amongst the groups. And if we just look at our data, we can see that, just sort of at a glance, it would be pretty reasonable to assume these guys were pretty close, average 440, average 483.3. There's probably not much of a difference there. This one does seem significantly different, 618.5. That's why we're going to build an interval that involves the 60 to 70-year-olds versus the 20 to 30-year-olds. So let's go ahead and do that on our next page here. So on our next page here for part B, we want a 95% confidence interval for average difference in reaction time between the 60 to 70-year-olds and 20 to 30-year-olds. All right, so since we're building a confidence interval for the average, we know it's going to be one of our quantitative confidence intervals. That means a one-sample confidence interval, one-sample mean confidence interval, a two-sample mean confidence interval, or a matched pairs. Clearly, this is not matched pairs data. There was nothing about test 1, test 2. And clearly, it is not one sample because we're talking about the average difference. So this is going to be a two-sample mean confidence interval. That's exactly why we developed that two-sample mean confidence interval. It was for estimating the average difference between two different populations. So we've got some conditions here, but the conditions for those quantitative ones are the same as the first three conditions we checked for the ANOVA. So we can just say, already checked. So we're all good with that. Then we can just move straight to the construction. For the construction here, we need to do x1 bar minus x2 bar plus or minus t star square root s1 squared over n1 plus s2 squared over n2. So there's a lot of things we need to know. We need to know x1 bar, s1, n1. We need to know x2 bar, s2, and n2. And then we also need to know t star. Notice that you can already sort of see this is why we took the time to write down the average and the sample size when we did our one var stat. We didn't need them from the ANOVA, but we are going to need them if we need to do any sort of follow-up confidence intervals. All right, now in the language of this, we said the difference in reaction time between 60 to 70-year-olds and 20 to 30-year-olds. So it looks like, just to keep it easy, 60 to 70-year-olds will be our group 1 and 20 to 30-year-olds will be our group 2. So let's bring over that information. The first set will be the 60 to 70-year-olds. So it looks like 618.5 and 189.3. So 618.5 and 189.3. And I believe the sample size was 13. Let's just confirm all that. Yep, so that was all the stuff from the 60 to 70-year-olds. And then 20 to 30-year-olds, we had 440, 123.5, and a sample size of 11. Notice that we're just completely ignoring L2, that the group of 40 to 50-year-olds, because it's just not mentioned that that's what we're going to be interested in here. So we're just using the 60 to 70-year-olds here, the 20 to 30-year-olds here. Now we need to find that T star. This is something we look up on table C. So we'll look up on table C. We know that our confidence level is going to be 95%, and we need to remember our degrees of freedom. Degrees of freedom for these quantitative procedures is usually the sample size minus 1. Remember that when you have two different sample sizes, you take the minimum. So we're going to take the minimum of 13 and 11 minus 1. The minimum is clearly 11, so when we subtract 1, we're going to get 10 degrees of freedom. And we'll just scoot this guy over so that doesn't look so weird. All right. So we've got 10 degrees of freedom and 95% confidence. Let's go take a look. If we do that there, we've got right here, there's our 95%. There's our 10 degrees of freedom. So it looks like our T star is going to be 2.228. So then we're going to get 2.228, and that'll be our T star. All right, let's throw all this stuff in here then. So we get 618.5 minus 440 plus or minus 2.228 square root 189.3 squared over 13 plus 123.5 squared over 11. When you're doing these confidence intervals for differences, you do need to make sure you go ahead and do that subtraction first. So let's go ahead and take care of that. It's going to be 618.5 minus 440. So it looks like we should get 178.5. So 178.5 plus or minus. Then, if you just type this in as it looks, you'll be all good. So 2.228 times, then use your square root, 189.3 squared divided by 13. Plus 123.5 squared divided by 11. And looks like we should get there about 143.4. Then do our subtraction, 178.5 minus 143.4. Looks like we should get 35.1. And then we can do our addition, 178.5 plus 143.4 is 321.9. So there we go. Now we can write our interpretation. We are 95% confident that on average, now again, we could say that this is just where the average difference lands, but since we did the 60 to 70-year-olds minus the 20 to 30-year-olds, this is how much more time it takes the 60 to 70-year-olds to react. So we can say 95% confident that on average, it takes 60 to 70-year-olds between 35.1 to 321.9 milliseconds more to react compared to 20 to 30-year-olds. So what we're saying here is we are saying that we are 95% confident that on average, again, got to have that phrase on average now, because when we're working with quantitative data, we're always studying the average. So 95% confident that on average, it takes 67-year-olds between 35.1 to 321.9 milliseconds more to react compared to 20 to 30-year-olds. So in other words, you could say that 60 to 70-year-olds on average are somewhere between 35.1 and 321.9 milliseconds slower than 20 to 30-year-olds to react. So there we go. Now we not only diagnosed that there was a difference using the ANOVA test, but then we used our confidence interval to sort of build an estimate for how big that difference really was. Alrighty, so that there gives you another example of running the ANOVA hypothesis test, as well as sort of some review on one of the older confidence intervals. That wraps up all of the sort of lecture videos for our class. There will be one more video after this that does a quick summary of all the hypothesis tests and confidence intervals that you guys have learned so far, but this is the last actual content video.